Okay, so we gotta get through this. Like I said, we're going over scientific method stuff, scientific thinking processes. Sometimes we call it scientific inquiry. This is basically scientific method, but we're going to identify the different elements of that, and then we're going to talk about theories, hypotheses. And so we just have to get through some things. Like I said, hopefully we get to do something fun tomorrow to actually use some of this, utilize some of this, and help you understand why some certain things are important. But just got to get going. So here's your first definition here. Observation. You're collecting information about a topic. Scientific method always starts with observation. In fact, most of your day-to-day interactions and the way that you deal with life starts with observations. When you showed up to school today, you probably saw one of your friends, and you could tell right away if they were having a good day or a bad day. Right? Some days they come in and they're not so happy and throwing their books in their locker and everything. You probably tiptoe around them a little bit so they don't bite your head off. Some days they're all happy and laughing and smiling, so you can just go right up and talk to them. That's great. But you do this all the time. You're always observing things. That's the way you interact with the world. You don't always collect that data and categorize it and start working with it scientifically, but you're always observing. That's a constant. Data is just a recorded observation. In fact, we were talking about that at the end of class yesterday. And we had two different columns of things going on. What did we have on one side for chalk observations? It's number stuff, like length, mass. But we also had other stuff, like what were those examples?
Chips.
Colored, chips,
Text.
texture, shape, describing that shape. Sometimes they're like spots of color, like you had the orange piece of chalk, but there was a blue dot on it somewhere, right? So lots of things over there too. But we also talked about what made those two different kinds of data different. Right? What was important? What was the important distinguishing factor between the two? Anybody remember? What made these ones different than these ones?
They had the numbers.
The numbers. Because they are specifically what kind of data, or how did you obtain them?
Through using tools.
Using tools, you measured them, right? These are measurements. Without an N, it's measurements, but whatever, you get it. So those are measurements, not measurements.
It's from New York.
Yeah, they're not from New York, just put an N in there, it's fine. These ones, though, are really important. The color, chips, texture, shape, spots. In fact, the color was your number one thing, right? That's what you used first. But if you were colorblind, it might not be so useful, right? These are dependent on what? Senses, what did you say? What looks. But they're also dependent on the way you perceive things, right? Because you perceive things differently than someone else. I don't know if you've ever thought about it before, but I always wondered when I was a kid, my favorite color is blue. I love blue. But if my favorite color is blue, it's probably triggering some kind of chemical signal in my brain when I see blue, right? How do I know? What's your favorite color, Jack?
Blue.
Dang it, what's your favorite color?
Green.
Green. Well, how do I know he looks at green like that? Maybe he has that same chemical reaction, right? It's a different color, but the same thing that he's responding to ultimately. So I never really had figured that out ultimately. Yeah, I wondered that as a kid. It was kind of weird. But maybe it's just the fact that you perceive that color differently that makes you have that same trigger in your brain. We're both responding to the same thing. It's just different stimulus. Right? That's what I always thought. And I probably didn't use those fancy words for it. But I was thinking, well, what if it's just I'm seeing blue, but you see the same thing I see when you're seeing orange, if that's your favorite color. right? It's just the way your brain perceives it.
I-
So these things are weird, right? They work really well for you. They don't necessarily work great for others, but they're still important. If you had to label those things, there are two different kinds of data, quantitative, qualitative. You figure out which one's which? Which one, Aspen?
Quantitative and qualitative.
Quantitative means you're going to see numbers because it's a quantity, right? An amount of something. So the quantitative, I know I have it backwards up on the board over there compared to here. You're always going to see numbers for those. Those would be your measurements, right? Measurements, depending on if you want to spell it correctly this time or not. Got it. Those are things that you're going to use a specific tool for in order to make that measurement. Right, there's water in here. I could measure that volume using a ruler because this is a regular shape, right? So I could use some math for a cylinder to figure out what the volume is. Or I could use one of these tools because it's a little bit more handy and just dump the water in here to measure how much there is, right? So this would be a little bit easier to do. But generally speaking, if I read that tool and Tucker reads that tool, as long as we halfway understand what's going on, we're going to get a similar answer. We're always going to get the same number. That's not always the case. In fact, I would guess that we probably won't get the same answer right now, but I have to teach my chemistry kids specifically how to use those because they don't know. Remember, there's different things you're looking at? Like that meniscus, where are you supposed to read that? The bottom of it, right? So, you would have had the right answer, right? But also, you're supposed to estimate one digit. So, we'll talk about that when it's important. But you can make measurements, but they should match no matter who's making that measurement. So these are usually pretty constant, pretty normal. Versus the qualitative ones, those are things that are completely dependent on your perception, right? It depends on how you view the world. So they're important, but they may vary from one person to the next. Yeah, but you use your senses to do this too. But, so you can't really say that quite. But these are things that can vary. They're not measurements, obviously, because those aren't supposed to vary. They depend on your perception. How do you perceive the world? Right? So if you guys could begin to associate those things appropriately, quantitative, qualitative. These were quantitative and qualitative backwards. I switched the order over there, but you can tell the difference. One has numbers, the other one doesn't. But these things are super important. If I'm doing a chemistry lab, I'm looking for certain things to know that a reaction happened. I'm looking for color changes. I'm looking for bubbles. I'm looking for, I want to feel heat, right, coming off of that. And all of those depend on your perception again, right? So they could vary from one person to the next. But if I did this experiment and I wrote down my observations, there are bubbles right now, and then Josh is trying to repeat that experiment, he gets to that same step, there's no bubbles, what's he probably going to assume?
He did it wrong.
Something's wrong, and he needs to try again. Maybe he screwed something up along the way. So those things are really important. Even though you can't measure them necessarily, you can actually measure the amount of gas that's produced. You can capture that gas and then measure the volume, and it can tell you something. But a lot of times those qualitative observations are important just because they can help somebody follow along. They can help them know whether they're doing it right or not. So you want to have both kinds anytime you're doing an experiment. But these ones usually, the measurements are typically the most useful in the long run. You can draw results from those a little easier. Draw conclusions, I should say. A hypothesis. First thing, you guys have a definition for this in your head because teachers have used it before. I have asked them repeatedly not to use this, but what is that definition you remember from like middle school?
What do you think it is?
Educated guess. do not like that at all.
You don't?
No.
Why?
I'll talk about it. This is my definition for hypothesis. This is a good definition for hypothesis. I'll tell you a 2-word definition, but this is what I would use. Testable statement that tries to answer a scientific question. Now what I want you to focus on here is this word versus this word. Why would one be better than the other? Anybody?
Because
Kayla?
Because, statement, you can be more like confident.
That it does emphasize confidence, right? If you're saying that you're guessing, that makes me think you don't have a clue what you're doing, right? That's the main reason why I hate this definition, is because that makes it sound like you don't know what's going on. If you're going to do an experiment and make a hypothesis, you better have some idea what's going on. You should have recorded and made lots of observations before you even attempted to do anything. So you should have a good idea what's going on. In fact, I just realized maybe I should be writing that over here, right? Educated guess. So that Castle can actually see that. Right? This word, guess versus statement. I really hate guess because it makes it sound like you don't know what you're doing. So I don't like that. But there's another important word in here that would make that definition way better as well. Is there another specific word anybody can point out that might be important? Addie? Testable. Thank you. You can't make outlandish claims unless you can actually test it. If there is no physical, tangible evidence for it that you can find, that you can look for, then it doesn't really belong in a science book. That's the point, right? If you can make all sorts of claims, anything you want, but unless you can test it, unless you can attempt to prove that by finding data that would support that hypothesis, then there's really no point in making that claim. So if you're going to do a 2-word definition for a hypothesis, I'd want you to say testable statement, not educated guess. I hate that. Now, if you say it, I can't actually take away your birthday or anything, but this is a much better definition. Yes.
It's Aspen Andrew's birthday today.
Like right now,
Yes.
so I won't take away your birthday. Happy birthday, guys. Okay, otherwise, do we need that? I'm trying to record here. Castle might want to sing to you later. Okay, so the other thing, usually they're written in if-then statements. Here, since I can't write on the other board. Insert page. I would usually want you to write a hypothesis like this. There are many other ways to write a hypothesis. This is just the easiest to keep track of your variables in. So you'll say if something, then this will happen. Right, so it's if blank, then blank, with a comma in between. That's an if-then statement. So this example right here, if you read that hypothesis, if I set my alarm 10 minutes earlier, then I will make it to school on time. I have a scientific question. I have a problem that I need to solve. What is that problem, obviously?
not getting to school on time.
Can't get to school on time. I don't have nearly as much problem as that with that anymore, but you could ask your band teacher how good I was at that in high school, right? I was late all the time. It was terrible, right? But this is a possible solution to that, right? And I can test this. I can find out if it works. So if I'm late every day, I'm supposed to be here at like 7:30, right? I think I actually was here at like 7:33 today, so I was late, no time. But if I set my alarm 10 minutes earlier, then in theory, I would get here 10 minutes faster, and that would be awesome. Then I'd actually be on time, and Calvin could find me when he needs me. But otherwise, right, this is testable, but you have to understand that you have to control certain things. I can set my alarm 10 minutes earlier, but what if I get up a little bit earlier, and then I decide, oh, I'm going to eat breakfast today because I got a little extra time, why not, right? Something that I wouldn't normally do. Am I gonna be able to get valid results?
Nope.
Maybe, I might still be on time. But if I'm not, do I know if it's because of the breakfast or because I didn't get up early enough? I don't know, there's no way to know. So, you have to, in an experiment, control conditions. So it's a process that tests a hypothesis under controlled conditions. I want to make sure that I keep almost everything the same except for setting my alarm a little bit early. Because I can't set my alarm early and then decide I'm going to walk to school instead of drive. Doesn't make any sense, right? Especially if I lived in Rushville. It wouldn't work very well. I can't decide, on the other hand, I can't wake up 10 minutes earlier and then get a ride to school instead of walking, like maybe you would do normally, right? Because then maybe you're on time because of the ride, not because you got up 10 minutes earlier. You don't know. So you make sure that you control as much as you can. Your independent variable is the condition that you manipulate, the thing that you change. So you got a blank to fill in probably, if you were spacing off. I'll come back to this
I
anyway.
was thinking.
But your independent variable, I'll go back to that so if you didn't get it. Always goes in this blank, if independent. So the thing that I changed in my hypothesis from before was the time that I set my alarm for, right? That's the thing that I changed. How many things can you change in an experiment?
One.
Just one. If you want to know what causes your result, you can only change one thing. You can do a lot of different experiments and change a lot of different things ultimately, but in one experiment at one time, you can only change one thing. So this is the thing that you change. It better only be one thing. If I make a delta like that, I mean change in science, so just get used to that. If I make a little triangle, I mean change. I use a lot of shorthand because I'm lazy, like I told you before. But my independent variable, that's the thing that you change, you manipulate it as the experiment. The dependent variable, on the other hand, is the results. That's what you're going to measure at the end of the day. That's the data you're going to record to decide whether or not it worked, your experiment. So what am I going to look for? What are the results I was trying to see in my experiment, my hypothesis?
If you get to school on time.
I want to be at school on time. But another major thing, remember that's dependent, that goes right here. It's called the dependent variable for a reason. It depends on, hopefully, your independent. It should be a direct result of that change that you make, which is why you can't change a lot of stuff, because then you don't know what caused that result. So my dependent variable should be that measurable result. It should depend on the independent variable. Right? And then we have constants. Yeah, those are the things that you don't want to change in an experiment. Those are all the other things that you're trying to keep the same. So in another example, I want to see how fertilizer affects plant growth. Right? So I have this plant, I put fertilizer on it, and I'm doing this to lots of different plants at the same time to make sure that it's a consistent thing, right? But I can't decide to alternately water. I'm going to water this one, and I'm just going to leave this one alone, and then water this other one, because that would be a whole different effect, right? So that'd be more than one thing that's changing. You definitely can't tell if that middle one that wasn't watered is not growing because the fertilizer sucks or just because you're terrible at taking care of plants like I am, right? You need to water it to be able for it to be able to grow, but you also need to water each plant equally. right? You gotta keep as many things constant as possible. They all need to be in the same conditions. If one's in the sun, the other one's not, that's gonna make a difference. If one's inside where it's cool and one's outside where it's warm, even if they're both in the shade, that's different. It's gonna make a difference. So you're trying to make as many things constant as possible. Got that? Easy enough? But then there's this other term here. Control. Which sounds like you're trying to make sure everything's constant, right? But when I talk about a control in an experiment, a control is actually what you use to compare your results with. So in my fertilizer experiment, I should actually have two different plants, give them all the same conditions, except for one gets the fertilizer, the other one doesn't. That way I can actually tell if one grew more than the other, right? If I don't have that control of the thing to compare it to, right, it grew. I don't know if it grew more than it was supposed to because I don't know how much it was supposed to grow. It's impossible to tell. You always have to have that thing to compare to. Right? So be careful when I say control, and I'm talking about a control in an experiment, it's specifically the part of it. It's the group that does not have that change so that you can actually compare your results and see what's going on. In my experiment, waking up early, my control really would have been my past results, right? If I was consistently late and now I'm on time all the time, then maybe waking up 10 minutes earlier was great. It was a good idea. So make sure you understand that when I talk about a control or a control group, that's the thing that you're comparing with. So in chemistry, I'll have two test tubes. One got the chemical, the other one didn't, just to make sure that the hot water bath isn't what made the color change happen, right? So one turns blue and the other one turns red, or one stays blue, the other one turns red. I know what caused my result. It wasn't just the heat, it was the sugar that was in there probably, if I'm thinking about Benedict's test, probably in my head right now. So you need something to compare so you can confirm your results. That experimental group, whoa, wrong thing, highlighter, green. That one's the one where you did make a change, but you have to have those two groups going at the same time. Sometimes you can't do that. Like in my example, I just have to look at past results versus future results to compare and decide. Okay, so this question, it's a whiteboard question. So I'll be looking around to see who has a good answer. If you are really intelligent, you see that these are coming, and I usually answer the question for you ahead of time. I definitely told you why you can't change more than one thing. So if you're paying attention, a lot of times you can get these out of the way early because there's a reason why I talk at you. It's not just to bore you. I'm telling you the answer. I never intentionally obfuscate. Obfuscate. My brain is not working. Weird word. So I need to see an answer for this. Why can't you change more than one thing? Why is it important that only one variable is changed? Okay. I actually saw a lot of good answers. I am looking for some specific wording. So there are a couple of them that could have been perfect, right? But the last one I read was pretty good. So Sarah, what was yours?
Because if change more than one variable, then you wouldn't know which change caused the results.
It is very important to be able to know what caused your results. And yes, you're right if you answered that it's going to screw up your experiment. Yeah, it does. But more specifically, you get to know what caused your result if you're only changing one thing. If you change two things, then you're not sure which one actually caused you to be late. Was it the not waking up early enough, or was it the eating breakfast? Right? If you have two things changing, it's actually impossible to know what caused your results. One thing though is to mention in biology, when you're studying living things, there are a lot of cases where you can't control a whole lot of things. And so it's really hard to do a true experiment where you can control every variable. Sometimes you have to go out where those living things are and just study them in their own environment, and you can't control things there. But if you collect a lot of observations and results, then hopefully you can eliminate some things here and there. So this is tough to do, but in a lab, you always want to change just one thing because then you can know what actually caused your results. Everybody understand that? Good? Okay, so theory, law. We already talked about a hypothesis. So see this question down here? I'm basically going to be explaining the answers as we go through. So make sure you're thinking ahead a little bit. Okay, so a theory is a proposed explanation for a wide range of observations, experimental results that is supported by a wide range of evidence. Very wordy, lots of stuff in there. Theory is one of those things that a lot of people get confused because when you hear theory, when you talk about if Jack has a theory about something, a lot of times, normal usage of that word, we think that he thinks this is happening, but he doesn't really know, right? So that's the way we would normally use that. But in science, if you're going to say theory, there's always a wide range of evidence. There's a mountain of evidence supporting this. Right? By the time it's a theory, we've never ever found any evidence that contradicts this. So we are as close as possible to sure that this is the truth. This is what's happening. So don't get that confused. Right? You got hypothesis from before. And again, I really should be writing on this board up here so that you could actually see that. We had hypothesis from before. The only difference between a hypothesis and a theory, for one, a lot of times there's more than one hypothesis that are lumped together to make a theory. There's more than one part to it, right? But also, the hypothesis may or may not be tested or confirmed yet, right? But a theory has lots and lots and lots and lots of evidence to support it. So hypotheses eventually turn into theories because of overwhelming support for them, right? So there is a difference between these two things, and mostly it's just the support, right? One is immensely supported. The other one, maybe Evan's got good evidence for it, but he needs to have somebody else confirm those results before we can really think that it's the real deal, right? So you're always looking for other scientists' peer review so that you can get more support. And otherwise, people can just write it off because we don't know. Maybe Evan's experiment was flawed, and maybe it wasn't. You'd have to test it separately to know that. But hypotheses do ultimately turn into theories, right? You just need lots and lots of evidence for that. Your law, on the other hand, describes a truth that is valid everywhere in the universe. Do you have that in parentheses there? No explanation for a reason. But a lot of people would assume that because of the way that we use those words, ultimately, that a theory turns into a law. Seems like a logical step, right? Hypothesis to theory, theory to law. But that's not really how that works. Right? Theories do not turn into laws. Laws were there always. They were there first. They came before the hypothesis. You guys know an example of a law?
Gravity.
Law of gravity. All it says is that if I let go of the marker, it's gonna fall. It's consistent results. It will always, always happen. Doesn't matter where I'm at, whether I'm here on top of a mountain, out in the middle of the ocean, on a boat, on the moon. Even when you're in outer space, it seems like it's floating, but it's technically falling. Because you're falling right now towards the sun. Because the whole Earth is falling towards the sun. But gravity works in general, right? All objects that have a mass are attracting each other. You're falling all the time. That's,
Related law, an object in motion stays in motion unless the
That's-
outside force acts.
that would be inertia, right? That's,
So you're saying
you're falling right now,
the
yeah.
sun's the
But because you're at a constant acceleration,
we're going to the sun, we're gonna die.
because you're moving at a constant
It's
acceleration.
like
in that
satellites.
context-
Satellites are always falling towards Earth, but they're
Yes.
in orbit.
How?
Exactly what I'm talking about.
So then they're not.
The only reason you don't think that you're falling right now is because it's a constant acceleration, so that force
So if it stops,
stops.
so
You
if
just
it
don't
stops,
notice
we're just
it.
like slamming on a wall.
Remember, the Earth is spinning at thousands of kilometers per hour. If the Earth stopped spinning, that's exactly what would happen to you right now. So, anyway, what I wanted to point out though is that a law is separate. Right? It's a whole nother thing. If anything, the law came first, and that's where I made my hypothesis from, making those observations, and then it turned into a theory ultimately. But laws are separate. They're their own thing. But a law doesn't try to explain anything. Just because when I throw something up, it comes down, what goes up must come down, just because that's always true, doesn't mean that that explains anything. Why did it fall? The theory would have a mathematical model to even explain that. Right? That force due to gravity is equal to some gravitational constant that I don't know, times mass A times mass B, divided by the distance in between those two things. That's how gravity works, technically. Right? You don't need to know that for a test, but just so you know, right, the theory of gravity includes that. It explains why two objects with a mass would attract each other. And it gives you an exact force as a result of that. Right? So it's trying to give you an explanation for why this is happening. This is definitely trying to explain why it falls. It'll even try to tell you how fast it's falling, how fast it's accelerating at least, right? So you can work with that kind of stuff. I don't even know if this is accurate, it's just something like that. It's as close as I can come just off of the top of my head. But theories try to explain why that phenomenon occurs. The law does not try to explain it, it just tells you that it's going to happen because it's always happened and you just see that. So laws really come first, they don't come last, right? So I don't want that down there, not really. They're separate from hypotheses, theories. These two things try to explain how that works. The theory is very complex, probably has multiple parts, but also has tons and tons of evidence to support. And this is probably the most supported law, or most supported theory, the theory of gravity, because we've done all sorts of things with that. And we can predict the motion of planets with it, and it works. So we're pretty sure that that's true. So otherwise, you guys had this question here?
Yeah.
And you're supposed to be able to tell me the difference between a hypothesis and a theory, and between a theory and a law. I think you could do that. So write it on your whiteboard, walk around and see if I can pick on somebody.
How about you look at the paper? I got it already written down. But should be able to, she can kind of see what we're doing,
No, there's no camera.
Oh, she can't see.
That doesn't mean you can flip her off.
right? Whoa.
Okay, Castle, we're flipping you off. Tucker's licking his nose. Oh God, Tucker, stop. That's gross.
That is not fun.
Oh, don't wipe it on me.
Get into this little cave. Rub up.
Oh,
three.
Mine goes for 2 cartons.
Or at least as much as you know, that will help.
Maybe 1.3.
Oh shit.
Dumb question.
At least answer one of them. So what was
Me and the dress nice, but also don't want to dress nice.
Oh. Yeah, number 5. 5.
Oh, that's my volleyball. You should wear that tomorrow. Actually, no, for my Are you seriously not gonna
Unless you're eating some grocery store. You sure it's lame?
That's what it's your board.
Curse? I might not know. I walked around.
Wait, you can feel it now, I'm sure.
Cut off.
Did you follow out?
You won't make
So, so I think I can get the first part. Right, the difference between a hypothesis and a theory, Max? Pretty sure you're on the right track, right?
No, I'm still writing it down.
You're still writing it? What was the difference? One word. There's one of the blanks that you filled in, the second blank you filled in, for the definition of a theory.
Theory is an explanation that's supported.
Supported. Right? The difference between this and this? Well, not ert. Is the amount of support that it has. Evidence. Right? I think that Caitlin's was pretty good for the theory and law. What was yours?
Laws are separate, while theories try to explain, laws don't.
Theories try to explain, laws don't. Period. Right? Laws are just there. Right? We observe them, we see them. But this specifically is going to try to explain. Whereas this thing doesn't try to explain anything, it's just an observation. Right? The law of gravity says that if I pull the chair out from under Brock, he's probably going to fall on his butt.
That's me, very.
I'm not going to do it, but that's what it says.
Just do it.
All right.